Good afternoon, dear students. Let us continue the class Ionic equilibrium. In this section, I wish to discuss about the ionic product of water. And hence, to introduce the concept of Kw, pH, pOH, pKa, and pKb. First of all, you have to consider the ionic equilibrium of water. Okay, now to discuss the ionic product of water, Kw, we have to consider the dissociation or ionic equilibrium of water. The water is peculiar that it has a auto dissociation. That is, one molecule of water combines with another molecule of water to form its own ion, that is hydronium ion and OH minus ion, which remain in equilibrium. This equilibrium is selectively known as the ionic equilibrium of water. When we apply the law of mass action to this ionic equilibrium of water, then the equilibrium constant K is equal to the concentration of hydronium ion into the concentration of hydroxyl ion divided by the concentration of H2O the whole square. Therefore, we can write K into H2O the whole square now become equal to H3O plus into OH minus. And you look, H2O the whole square is a constant because the self-dissociation of water is extremely small, approximately 5,000, 1 in 1,000, 5,000 part. Okay, approximately 1 mole in 5,000 part of it. So that the concentration of H2 remain almost constant. Therefore, we can write or rewrite K into H2O the whole square is a new constant, that is Kw, the ionic product of water. Why that is called ionic product of water is that because it represents the product of the ionic concentration of water. Okay, it represents the product of the ionic concentration of water, that is H3O plus into OH minus ion. Hence, that product is normally known as Kw or ionic product. Okay? Therefore, the ionic product is defined as the product of hydronium ion and hydroxyl ion for any aqueous system. Okay? It is always a constant for any aqueous system. That is for it is constant for water as well as for any aqueous system. And when at a temperature or when the temperature is at 25 degrees Celsius, okay, it is a constant at a constant temperature. When T is at 25 degrees Celsius, then the value of Kw is equal to 1.00 into 10 raised to minus 14. Okay. It is not unit, it is merely a constant. Therefore, Kw is equal to 1.00 into 10 raised to minus 14. This is the value of Kw of any aqueous system at 25 degrees Celsius. If you consider a pure sample of water, that is the distilled water for us, the peculiarity is that the concentration of the hydronium ion is equal to the concentration of hydroxyl ion. Okay, that was found to be equal to 1 into 10 raised to minus 7 moles per liter each at 25 degrees Celsius. Okay, each are 1.1 into 10 raised to 7 moles per liter. Such a sample of water, that is the distilled water, is said to be neutral because the concentration of hydronium ion is equal to the concentration of OH minus. Okay, that is the neutral sample of water in which the concentration of both hydronium ion and OH minus ion is equal, that is 10 raised to minus 7 moles per liter each. Then the pH scale. Okay, the scale was introduced by Sorensen to express the acidity or alkalinity of a aqueous system in terms of the power of hydrogen ion concentration present in the solution. Okay, and it is mathematically defined as pH is defined as equal to the negative logarithm of hydrogen ion concentration to the base 10. Okay, that is pH is equal to minus log H3O plus to the base 10. Therefore, the H3O plus ion concentration is equal to 10 raised to minus pH. As you know, for any acidic solution, the H plus ion is greater than 10 raised to minus 7 moles per liter. Okay, that means that is 10 raised to minus 6, 10 raised to minus 5, 10 raised to minus 3, etc. up to 10 raised to minus 7. Therefore, pH is lesser than 7, that is acidic. Okay, pH becomes lesser than 7, that is acidic. For any basic system, any alkaline or basic system, the hydroxyl ion concentration is greater than 10 raised to minus 7, that is 10 raised to minus 6, 10 raised to minus 5, etc. Therefore, the H plus ion concentration becomes lesser than this. Okay, therefore pH is greater than base 7 for basic system. That is, pH is greater than 7 for basic system. Then for a neutral aqueous system, the H plus ion concentration is equal to 10 raised to minus 7 moles per liter, that is exactly equal to OH minus ion. Therefore, pH is 7. Therefore, that is a neutral. Okay. Just like pH, we have another scale, that is pOH, that is defined as minus log OH minus ion to the base 10. Simply, pOH is equal to minus log OH minus ion concentration of base 10. Similarly, we have pKW. Okay, that is the negative logarithm of Kw. So, negative logarithm of Kw. And further, the sum of pH and pOH is always equal to pKw. Please you write or study. pH plus pOH is equal to pKw. That means pH plus pOH is equal to 14 because pKw is 14 for any aqueous system at 25 degrees Celsius. So, an assignment, please derive the expression that I have just mentioned, that is pH plus pOH is equal to 14 or pKw from Kw water for any aqueous system. Okay, you please work out the problem or derivation as an assignment. Okay, let me continue the class. Buffer solution and the pH of buffer solution, that is very important in the examination viewpoint. You can expect a short essay from this part. A buffer solution, that is a solution whose pH does not change even by the addition of acid or base into it. Or we can say it is a solution having reserved acidity or reserved alkalinity. Okay? A buffer solution, on the other hand, is a solution having a reserved acidity or reserved alkalinity. There are two types of buffer. One is acidic buffer having a constant pH below 7. Okay, example, acetic acid plus sodium acetate. is an example with a pH 4.9. And second is a basic buffer having a constant pH above 7. Example, ammonium hydroxide and ammonium chloride with a pH 9.4. In each case, you have to remember one important point, you have to note one important point. That is, an acidic buffer is a mixture of weak acid and the salt or the weak acid with a strong base. On the other hand, a basic buffer is a mixture of weak base, ammonium hydroxide, with the salt of it with a strong acid. Then buffer mechanism, or how the buffer works on the addition of an acid and a base to resist the change in pH. That is a buffer mechanism. Let us consider typically an acidic buffer consisting of acetic acid and sodium acetate as a typical example. In this buffer, as all of you know, acetic acid is a weak acid and it undergoes partial ionization to its ion, that is acetate ion and H plus ion, and it remain in equilibrium. It is a partial dissociation or ionization and it is an equilibrium. But the other component, that is sodium acetate, is a salt. It is a salt. It has undergone full ionization or dissociation, or it is fully dissociated into acetate ion and sodium ion. That is the situation in the case of the buffer solution. So, when you are going to add an acid into it, you are going to add an acid into it, like HCl, like a HCl. Adding acid, the added H plus ion combined with acetate ion, combines with the acetate ion to form feebly ionized acetic acid, to form feebly ionized acetic acid. To form feebly ionized acetic acid, CH3COH. Once again, the added H plus combines with the acetate ion to form the feebly ionized acetic acid, thus keeping the pH constant. But on adding a base into it, that means hydroxyl ion, the added OH minus ion, the added OH minus ion get neutralized by acetic acid directly. Get neutralized by acetic acid directly to form undissociated water molecule, to form H2, to form H2O, and thus keeping the pH constant. That is the buffer mechanism. Hope that you understood. All of you have understood the mechanism. I am giving you an assignment for, that is, explain the mechanism of a basic buffer that is resisting in the change in pH. You explain with the typical example with respect to ammonia hydroxide and ammonium chloride as an assignment. That is over. Let me stop now.